Okay, so what I want to go over today is the last section in chapter 9, which is on, we're looking at testing claims about um, two population standard deviations or two population variances. The, the, the hypothesis test that we use is the same in either case. So they're basically the same. Okay, so we need a new kind of distribution in order to work out this kind of problem. So just remember, we've got several distributions that we've talked about at this point. Of course, the normal distribution, the bell-shaped one, is very common. We talked about the t-distribution, and then we talked about the chi-square distribution. And now there's one more distribution that we need to talk about, and it's called an F distribution. So I want to talk about that first, and then we'll work out a problem where we have an F distribution. Okay, so basically an F distribution, looks like this. It's not symmetric. And the values of F start at 0. So these are going to be called F values, I guess. Just like in a t distribution, these are called t scores. In an F distribution, these are called F values. Um, they start off at 0 and they go to infinity. It's not symmetric, so there's no symmetry to it. This peak is shifted to the left. And then the shape of this distribution changes depending on the sample size. We're going to have two populations that we're going to be sampling from. And so you're going to have, a sample size for the first one, which we'll call N1, whatever that is. And then we'll have a sample size for the second one, which we'll call N2. The degree of freedom for this one is one less than the sample size. So it's N1 minus 1, and the degree of freedom for this one is also one less than the sample size. So it's N2 minus 1. So the shape of this distribution changes depending on what the degrees of freedom look like here. So just be aware that this shape changes a little bit depending on how big these two degrees of freedom are. They alter the shape of this a little. So that's kind of the basic idea of an F distribution. It looks very much like a chi-square distribution. Like chi-squared starts off at 0 and goes to infinity as well, and it's not symmetric. The F distribution is not exactly the same as a chi-square distribution. It's slightly different, and like I said, the exact shape of this distribution changes a little bit depending on the two degrees of freedom here. Okay, so having said that, this is the kind of distribution we're going to need in order to work out the kind of problems in this section. So let me pull up the problems from the homework, and I'll show you how we can work it out. Okay, so I'm going to let's look at number 3 from the homework. Okay, so this one says the accompanying table gives results from a study of words spoken a day by men and women. Assume that both samples are independent random samples from populations having normal distributions, and we want to use a 0.05 significance level to test the claim that the number of words spoken in a day by men vary more than the number of words spoken in a day by women. So the first thing I want you to notice is, first of all, this is a claim. So that's why, we're going to do a hypothesis test to test the claim. But what they're claiming is that the number of words spoken in a day by men vary more than the number of words spoken in a day by women. It's not a claim about the mean number of words spoken in a day. It's a claim about how much the number of words vary. And so they think, so kind of what this is they're getting at is they think that some men that don't talk a lot, so they don't speak, don't use a lot of words during the day or speak a lot of words during the day. And then there's some men that speak a lot. So there's a lot of variation in the number of words spoken by men. Whereas women, I guess they're saying there's not as much variation. Like women talk a little bit, uh, maybe a little bit more, but the variation is not as great as for men. So there might be men that don't talk a lot, and there might be men that talk a lot, and that creates a lot of variation. Whereas for women, they're claiming that there's not as much variation in the number of words that they speak in a day. So to test the claim, they took some samples. Okay, so uh, let's paint a picture of what's going on here. So you got two populations, um, men and women. Actually, the number of words, well, words spoken by men, but you get the idea. And if you were able to collect data on all men and how many words they speak in a day, you could calculate the standard deviation and the number of words that they speak. Okay, so we label that with the sigma sub 1. And then you could do that for women, and that would be labeled sigma sub 2 here. Okay, so the claim has to do with um, the two sigmas here. Actually, you can also square these numbers, and it's called variance. So if you square them, this is called, if you don't square them, these are the standard deviations. And if you square them, they're called variances. So the claim is, so let's start hypothesis test. Claim is that um, number of words spoken in a day vary more for men than for women. So the variance, they're claiming this variance here is greater than this variance here. Right, so there's our claim. And that, of course, that's the alternative hypothesis, right? Because it doesn't have the equal sign in it. Then the null hypothesis is technically um, sigma 1 squared is less than or equal to sigma 2 squared. Um, let's take a step back. I forgot about something. Usually, population that you label 1 and 2 doesn't matter. It's arbitrary. In this case, it actually matters. I forgot about this. So let me mention something first. You can't just arbitrarily pick which one to be 1 and 2. You actually have to look at the sample to decide that. So let me write down the sample information. So to test the claim, they sample a certain number of men. They sample 185 men. And they look at how many words each man speaks during the day. They record that, and then they average them up, and it averages to 15,667.5. So that's X1 bar. Then they look at the standard deviation. By the way, I shouldn't label these yet, so let's leave this unlabeled. They look at the standard deviation in those the words number of words spoken for the 185 men, so you get your sample standard deviation, and is 8,632.4. Okay. And then they sample the women. 209 women. The average number of words spoken by those women was 16,214.3. And I shouldn't label this yet, so leave these unlabeled for the moment. And then the standard deviation in those for the women, the sample standard deviation was 7,301.3. Okay, so to test the claim, they sample the men and they sample the women, right? And this is what they get. Now, this is where you can't just arbitrarily pick population one to be men or women. You have to decide it based upon one that has the larger sample standard deviation has to be labeled one. So if you look at these two sample standard deviations, this one's the larger one. That one is the one that's labeled one. So the larger one is labeled as S1. And so everything is, now this is labeled one, everything's one, so this is population one. Population one would be men, only because they have a larger sample standard deviation. You can't arbitrarily pick men to be two. Men have to be one. It's important that you do this. The one with the larger sample standard deviation has to be labeled one. And then the one with the smaller sample standard deviation is labeled as two. Okay, so I got lucky because I didn't look at this first. You need to look at the sample standard deviation first. Look, see which one's larger, and whichever one's larger is labeled as one, and then the one that's smaller is labeled as two. So do that first. Okay. So this does turn out to be population one men, and this does turn out to be population two women, but I should have started down here and looked at this first. Okay. So just keep that in mind. That's important. Okay, and then you set up the hypothesis test, and it looks like this. And remember, we usually just think of this as being equal to. Okay, and now we're going to run the test. Now let's do the traditional method first. And then we'll do the p-value method. Okay, so the traditional method, first of all, this is going to be an F distribution. So it's going to look like this. And then they told us they wanted to use a 0.05 significance level, right, to test this particular claim. We're testing at 0.05. Okay, and you can see that this is going to be a right-tailed test. This arrow is pointing towards the right. If it was pointing towards the left, it'd be a left-tailed test. And remember, if this was a not equal to, then you'd have a two-tailed test, and you'd have to divide this equally among both tails. All right, but we have a right-tailed test with this much area in the right tail. Okay, and then the critical value, remember when you do the traditional method, the first thing you do is find the critical value, which is the boundary here. So we're going to figure out what F value, now remember these are F values, we're going to figure out, it starts off at 0 and it goes to infinity. we want to figure out what F value has this much area to the right of it. And that's going to be our critical value. Okay, and you have to do this on the table. Unfortunately, there's nothing on the calculator that does this. So I just pulled up a F distribution table. You can Google this if you want, or use the one in the book. The first thing you need to look at when you look at an F distribution is what alpha is in the right tail. So in this diagram, they're calling alpha the area that you have in this right tail. So this first table is if alpha is 0.1. That's not what we have. We have 0.05 in the right tail. So we'd skip this first table. It's not what we want. But then if you go to the second table, that's exactly what we're looking for, right? The area in the red and the right tail is 0.05. And so this is the table that we need. If you keep scrolling down, there's another one that says if the area is 0.025 in the right tail, you would use this table, okay? And then 0.01 in the right tail. So you need to find the correct table first, okay? And this is the correct table for us because that's the amount of area we have in this right tail. Then as degree of freedom 1 and degree of freedom 2. And that has to do with, I didn't write these down. This is 1, and the degree of freedom for 1 is 1 less than the sample size for this one. So it's going to be 184. Whereas over here, the degree of freedom for the second one would be 1 less than the sample size here, which would be 208. Okay. Again, this one's labeled 1, right? This one's labeled 2. So it's important that you get the labeling correct. Remember, 1 is has the larger sample standard deviation. It matters on the table. All right, so we have DF1, degree of freedom for the first one is 184. And just notice that, don't put all the numbers on here. So you just have to pick the closest one. And I would only pick infinity if it was like way bigger than 120. Okay. 184 is close enough to 120 that I would just use 120. I would only use the infinity one for like a really large degree of freedom, something like, 1,000 or something. But 184 is close enough to 120 to just use 120. So I would use 120. And then the other one was, I guess, 208. So DF2 is 208. And that would be on this column here, right? The left column. And again, the closest thing would be 120. Again, I wouldn't use infinity unless it was like above 1,000 or so. So I'm going to use 120 and 120. So if you look at 120 and 120, the F value is 1.3519. Because 120 is this column here, and 120 is this row here. And that leaves you with 1.3519. So that's your critical value. Okay, and now we're going to run the test. Remember, this is the boundary that we use to decide, whether we're going to reject null or fail to reject null. And now we're going to actually run the test and see what happens. Now, remember, when you run the test, the first thing you do is you assume the null hypothesis is true. The test is based upon that assumption, which is we're assuming that the same. Population standard deviations here and here. We're assuming that they're the, variances or whatever, standard deviations or variances. We're assuming those are the same. So we're assuming the population variance over here is the same as the population variance over there. Okay. And then the test statistic, We're going to find the test statistic for this, and it's going to be S1 squared over S2 squared. What we're going to do is we're going to find the ratio of this variance to this variance, the sample variances. But S1 is the larger one. So the reason we picked S1, the reason we picked the larger one to be 1 is because we want the larger one to be on top when we create this ratio. Okay, so that's the reason we picked this one to be 1, because it's larger than this one, to ensure that the top is larger than the bottom here. And then the thing we get is called an F value. Okay, so what we need to do is take 8,632.4 and then square it to get the sample variance, and then divide it by this standard deviation squared to get the variance for this sample. Okay, so whatever that is the F value. Now remember, this is just the standard deviation, right? You have to square it in this formula, right? So you're actually taking the variance, the sample variance here and the sample variance here, which means you have to square this and you have to square this. So it's the sample variance divided by the sample variance. All right, anyway, let's see what we get. 8632.4 squared divided by 7301.3 squared. Okay, so we get 1.398 if you round it off. I'm just going to round it off. 1.398. That is our F value, which is our test statistic. Okay, and so you can see what happens. The test statistic lands a little bit beyond 1.35, right? It lands a little bit beyond there, 1.398. So it lands in the critical region, right? And if you remember, if the test statistic lands in the critical region, you reject the null hypothesis. So I don't believe null hypothesis. I don't believe these are equal. I'm rejecting that. And why am I not? Why do I say I don't think they're equal? Because these two numbers are the two sample variances here are far apart. How do I know they're far apart? Because when I took the ratio of the larger one to the smaller one, the ratio, it's basically just the ratio, right, of the two sample variances. Ratio is 1.398. And we already predetermined up front anything that has a ratio of more than 1.35 is going to be too far apart. So we're comparing ratios here to decide whether they're far apart. In the past, we would have subtracted them and found out how far apart they are in terms of uh, subtracting them. Now we're looking at the ratio of the two numbers to determine how far apart they are. And in this case, the ratio of the sample variance here to the sample variance here is about 1.398. And we determined up front that anything more than a ratio of 1.35 is when we're going to say that they're too far apart to believe. So the reason I'm rejecting this assumption that they're equal, like sigma 1 squared is equal to sigma 2 squared, is because S1 squared and S2 squared are so far apart. The ratio of S1 squared to S2 squared is 1.398. So they're not close enough. These are not close enough to believe that these are equal. That's why we're rejecting this assumption. You have to follow this up. After you decide whether you reject the null or favor the null, then you have to decide what that says about the claim. And in this case, that would support the alternative hypothesis if you reject this one, right? If you reject this, you're supporting the alternative, which is supporting the claim. So yes, there's evidence to support the claim. Okay. And that's how you would do the traditional method. Now, just for the fun of it, these had been closer to each other. Let's just play with this a little bit. Um, let's suppose these were the same numbers. So let's suppose this was 8,632.4, just for a moment. Let's say the S1 is the same. All right, S1 is this, but S2 is now this. So these are the same. When you take the ratio of those two numbers, you're going to get 1. So S1 squared divided by S2 squared, where I'm supposing that S2 is now the same as this, right? 8,632.4. Then this would end up being 1, right? S1 squared over S2 squared would give you a 1. And that would land right here in the middle. 1 is right there where the peak is. So now you don't land in the critical region because your test statistic is here. And now you fail to reject the null hypothesis. And the reason you're failing to reject it is because it seems reasonable that these could be equal. Why do I say that? Because the two sample variances were the same, right? So if these are close to each other, right, if S1 is close to S2, then you might think that sigma 1 squared is equal to sigma 2 squared from the populations. That's what would happen in this case. So you cannot reject the null hypothesis. You're failing to reject it. And if you can't reject this null hypothesis, you cannot support the alternative hypothesis, which happens to be the claim. So then you would say there's not enough evidence to support the claim. Right? Not enough evidence in that case to support the claim. So that would be the other situation. Okay. All right. So that's the traditional method. I'm going to go back to the original problem. So let's ignore what I just made up as a alternative scenario and go back to the original test statistic. And now let's do the p-value method. Okay, so the original test statistic was this. We ended up rejecting the null hypothesis, and then that means there wasn't enough evidence to support the claim. Now, we should get the same answer when we do the p-value method. Okay, so the p-value method, if you remember, you don't bother finding the critical value, so we don't bother finding this. All we do is we run, we go through the test, we run the test, we assume the null hypothesis is true, that sigma 1 is equal to sigma 2 squared, sigma 1 squared is equal to sigma 2 squared. We assume that's true. And then find our test statistic. So all that stays the same. What's different is then you locate the test statistic on the distribution, right? You're not finding the critical value, right? So you ignore that, but you do find the test statistic here on the distribution. So you locate it, it's right here. And then you're going to find the area either to the left of this test statistic or to the right of it. And that all, how do you know whether you go left or right? It's based upon your alternative hypothesis. So this is pointing towards the right, so you're going to find the area to the right of it. This had been pointing towards the left, you'd find the area to the left of it. And if it's not equal to, you would find the area, you know, an area to the left and an area to the right, and the smaller one, whichever smaller, then you would double it. Remember, in a two-tailed test, you have to double the area in the tail of the test statistic. So you have to decide which side is this closer to the right or to the left tail. So you'd have to figure out how much area is in here versus here. and whichever one is the smaller one, you would take that area and then double it to get the p-value. Okay, but anyway, that's if you had a two-tailed test. We have a right-tailed test, so we're going to find the area to the right of it. And we can do this on the calculator. So go to your distribution button and you scroll down until you see F, CDF. This is no different than what we've had before. We had a chi-squared CDF, we had a normal CDF, we had a T-CDF, there's also an F-CDF. And it's the same idea. It's going to tell you the area trapped between two F values. Okay, and the lower F value is 1.398. And in this case, the upper one would be infinity. I'm just going to put in a bunch of nines. Now, one thing you got to remember though is you got to put in the degrees of freedom, and there's two of them now, and you do them in order. So N1 minus 1 is first, and then N2 minus 1 is second, or DF1 is first, DF2 is second. So let's go back and look. DF1 is 184. That comes first, and then DF2 comes second. And that was 208. All right, and so this is going to give you the area trapped between those two F values. It's 0.0095 or 96 if you round it off. So and since this is a one-tailed test, that would just be your p-value. You don't have to double it. If it, if this was a two-tailed test, you would double it, but it's not. It's a one-tailed test. So this is your p-value. The way, if for some reason this was less than, you would have found the area to the left of the test statistic, and then you would have started off at 0. So lower number would be 0, and then the upper would be 1.398. But that's if you find the area in to the left of this. Okay. We were finding the area to the right of it, so it went from 1.398 up to infinity, right? The lower is 1.398 and the upper is infinity. So it just depends on whether you're finding the area to the right or the left as to what you put in the calculator. All right, so then finish this off. You compare the p-value to alpha. So alpha was 0.05. You can see the p-value is less than alpha. This number's smaller than this one, right? And if the p-value is smaller, then you reject the null hypothesis. If the p-value is smaller than alpha. So we get the same answer. You reject the null, and then, of course, same thing happens. If you reject the null, you're supporting the alternative, which happens to be the claim. So you're supporting the claim. So you get the same answer as you did before. Okay, let's just double check this. Oh, I didn't show the completed problem, so I guess we can't check it. Well, let's put in the answers. All right, so let's just go through this. So this is the correct setup. Our F value, our test statistic, see what that was, 1.398. That went to rounded 2 decimals. So if you round that to 2 decimals, it would round to 1.40. And then the p-value is 0.0096. But if you round it to 3 decimals, this would round to 0.001. Sorry, 0.001, right? That 0.01, sorry. So you'd round this to 1. So 0.010. All right, so that's your p-value. And then the conclusion would be, regardless of which way you do it, whether you do the p-value or the traditional method, the conclusion was we rejected the null, and that means there was sufficient evidence to support the claim, so it must be D. Okay, so that's how you do that one. By the way, you should reflect on whether the conclusion that you're getting makes sense. We concluded that sigma 1 squared is greater than sigma 2 squared. That was we're supporting that claim, right? And when you look at the sample data, this is so much larger than this. That's why you're supporting someone's claim, right? If you look at it in those terms, it makes sense. So just kind of reflect on it and see if it makes sense before you put in the answer. But yes, this is so much larger than this that we believe this is larger than this. So that's why we're supporting your claim, okay? Okay, one other thing, and then we're pretty much done. You'll see in the homework, like when you get to number 5, this one says, listed below are time intervals in minutes between eruptions of a geyser. And then they look at ones in the past few years versus the ones from 1995. And this is what they came up with. So this is their sample data. So the recent eruptions, these were the times between the eruptions in minutes. So 74 minutes between one eruption and the next, right? 91 minutes between one eruption and the next. So they're randomly sampling them. And so these are the recent intervals, and then these are the ones from 1995. And I guess they're sampling 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 from the recent currently, and then 12 from the past. Okay, and so the claim is they say, does it appear that the variation of times between eruptions has changed? So they're not actually making a claim. They just want to know whether does there appear to be a variation between the times. But I want you to use a 0.05 significance level to test. They're not really making a claim. But the way you would set this up is, again, you got two populations. One of them is going to be recent, the other is going to be the past. But I'm going to hold back on labeling them because remember, the way you label this depends on S1 and S2. So, but the claim is that the variation in the eruption times is either the same or they're different. So in other words, someone would either claim that the variance here is the same as the variance here, or they're different. And when you set up your null hypothesis and your alternative, null hypothesis is that they're equal, the alternative hypothesis is that they're not equal, then you can claim whichever one you want to claim. You can claim that they're not equal, or you can claim that they're equal. They actually didn't make a claim here, which kind of bothers me. But whatever you claim, you would put the claim next to it. Okay. All right, so then what's different about this problem is they don't give you the sample information. So you need to know S1 and S2. The sample sizes are, like I said, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you're sampling 12 from each. So you already know that. So when you look at the samples, they're both size 12. The thing we need that we don't know is their sample standard deviations. So that's where you would go to the calculator and just type in the raw data. So you just type in all these numbers into L1, then go to one variable statistics. Maybe I'll do that just because it's important that you pick the right population 1 and 2. So let me just put this in real quick. So you just type these in to L1. And then after you do that, you go to one variable statistics. So you go to stat, calculate one variable statistics, and then it will tell you S sub X, right? Sample standard deviation for this is 12.158. So the recent is 12.158. That's the sample standard deviation for the recent. And then you got to look at the past. Let me see something for a second. I think there's an F test on here. Let me just see. There's a two sample F test. And if you could put in the statistics, if they give you the summary statistics, you could put those in. So I could have done that with the last problem. So you could put in, N1 and SX1, N2 and SX2. And then the last one we did was greater than. So you select greater than, sigma 1 is greater than sigma 2. And then you calculate, and it would give you the test statistic and the p-value. But I'm going to go ahead and select data. Notice when you select data, they want you to put one of them in L1 and the other in L2. So I'm going to go ahead and yeah, the problem is I can't do standard deviation on this one. Yeah, I'm going to do it without the F test, okay? Because I want to show you something. So I'm going to put, if you're going to use the F test, you put one of them into L1 and the other into L2, and then go to the F test and just pick L1 and L2. But I can't do one variable statistics from the L2 column. So I'm going to put this one into L2, L1. So I'm going to clear this out, and then I'm going to put this into L1 instead of L2. And the reason I have to put it into L1 is because when I go to stat calculate one variable statistics, it doesn't give me the option to pick L2. It automatically takes everything from L1. And so the sample standard deviation for the L1 column, now that I've changed it for the past ones, is 9.478 or 9.477. So let me write that down. So this one's 9.477. So this is where you would look at the two and you'd say, okay, this one's bigger. So this one has to be labeled as 1. This one's labeled as 2. That's why I did it this way. So then that's going to tell you which one's 1 and 2. So 1 is the recent and 2 is past. And then S1 is 12.158. S2 is 9.477. By the way, you don't need to know the sample means. This is not required. It doesn't matter what the sample means are, so don't worry about these. I mean, you could have written them down if you wanted to, but don't change anything in the problem. So then you'd go and run the test. Okay, so here's your so here's your null and alternative hypothesis. And then you'd run the test. Let's just do the p-value method. So you assume H0 is true. That sigma 1 squared is equal to sigma 2 squared. And then you find your test statistic, which is simply S1 squared divided by S2 squared. Okay. And so I'm just going to do that on the calculator and see what we get. Okay, so you get 1.646. I'll just round it off. So that's your test statistic. And then let's find the p-value. So the hard part is knowing, here's your test statistic. Now you've got to decide whether you're going to find the area to the left or to the right of this. I think is okay. I think the easiest way to figure this out is 1 is in the middle, I think. So if it's to the right of 1, then you're going to find the area to the right of it. If it's to the left of 1, you would find the area to the left of the 1. So I think you're going to end up finding the area to the right, but we'll double check this, okay? You'll know because if this is more than 0.5, then you should have found the area to the other side. Because when you double something more than 0.5, you'll get something more than 1, and a probability can't be more than 1. And remember, the p-value is a probability. And remember, you're doubling it too, right? Because it's a two-tailed test. So let's see what we get. Go to distribution, FCDF. From 1.646 up to infinity. And now your degree of freedom would be 11 in both cases, right? DF1 would be 11, DF2 would be 11, one less than the sample size, right? And 11 comma 11. So the area trapped between, those two F values is 0.2107, I think it was. Yep, but that's not your p-value because that's simply the area trapped in this right tail. And by the way, if you had found the area from 0 up to 1.646, you would have gotten something like 0.79, which is more than half. When you double this, it would be more than 1, and that's when it doesn't make any sense because the p-value can't be more than 1 because it's a probability. probabilities can't be more than 1. So it must have been the area to the right, which we picked correctly. You double this though, right, to get the p-value. So it's actually 2 times that area. So the p-value is something like 0.4214 when you double it. And then I guess we're testing at 0.05. And so you can see what's going to happen. The p-value is greater, alpha, and when that happens, you fail to reject the null. And they didn't make a claim about either one of these, so we're just going to leave it at failing to reject the null. There was no make. If you look at the problem, no one made a claim here. They just asked us to determine what we think is probably the best answer here. So failing to reject the null means that it seems like, these could be equal, right? I can't reject the idea that these are equal. So if you ask me, which one, I would go with the one where I think they might be equal. But let's just see what they got here. So 1.65 was the test statistic. I believe that's what we got. 1.65, right? If you round it off to 2 decimals. The p-value is 0.422. If you round that off to 2 decimals, it's probably because it's slightly off, but it's because I rounded this off a little bit. It would have rounded to 0.422 if I didn't round this off from the beginning. So that's just a rounding error on my part. So that's the p-value. And then we fail to reject null. All right, I guess they are making a claim, but they're not making it clear what the claim is. It says to support the claim that the variation of times has changed. So they're claiming that they have changed. All right, didn't say that. But. So if you go back and look at it, I guess they're claiming this is their claim. There was a change in the variation. Okay, so if you fail to reject the null hypothesis, then you're not able to support the claim, right? That would be the conclusion. So fail to reject null, there's not enough evidence to support the claim. Okay. Now, the only thing I want to mention is you could have done this, like I said, using go to stat tests and then scroll down to the F test, 2 sample F test. And so the options are you could have put one of them into L1 and the other into L2, then just selected data and then scrolled down to here. The frequency's at 1, right? So these should be 1. And then you would select not equal to, because that's your alternative, and then calculate it. Okay. But remember, I didn't put one of them in L1 and L2. I put both of them into L1 just because I wanted to do one variable stats. So the other option is to put in the summary statistics. So you'd select stats, and then you could just put in sample data. Okay, so I'll just do that real quick and show you that we'll get the same answer. So N1 was 12. S1 was 12.158. Now this is rounded, so that may give us a little bit of an error, but shouldn't be that far apart. N2 was also 12. And then S2 is 9.477. Again, that's rounded off, so it may not be as accurate. Could be. And then again, you'd select, not equal to, because that's our alternative hypothesis, and then you would calculate it. And there's your F your test statistic is the F, right? 1.64 or 1.65 if you round it off. There's your p-value, 0.421, 0.422 if you round it off. So you get the same result, okay? So honestly, if I did this problem by hand or from the very beginning, I probably would just this one into L1 and this one into L2. And then I would just go to F, the two sample F test and select um, data. I would have entered the data into L1 and L2, and I would have done it that way. The way I did it was I calculated S1 and S2 by going to one variable statistics, right? I put one of them into L1 and found the sample standard deviation using one variable stats. And then I put the other one in L1 and went to one variable statistics and found the sample standard deviation for the other one. And then I calculated it from there. It probably would have been a little bit easier if you had just put one into L1 and the other into L2 and then gone to data. Okay. I wanted to show you, you know, the full-blown problem step by step in case you have to do it by hand at some point. Okay, so anyway, that's how you work that kind of problem. All right, so I guess that's it. Does anybody have any questions though before we end it? Okay, so this is I guess the end of chapter 9. So there's, that's the end of the two population hypothesis tests. And just a quick review, there's only 3 cases. You're either making a claim about 2 population proportions, and that was 8.2, 2 population means, that was 8.3, or 2 population standard deviations, or variances, and that would be this section, okay? And then the next couple of days we'll cover, there's 2 sections in chapter 10, we're going to cover 10.1 and 10.2, so we'll do that Thursday and Friday, and then on Monday we'll cover 11.1, and that'll be sort of the end of the course. And then the test will be due, I guess, by Wednesday night, test 4 over chapter 9, 10, and 11. And then the final exam will be due by Thursday, okay?